An enormous privilege and pleasure to be able to welcome Professor Lord Martin Rees. In many ways needs no introduction. He's the Astronomer Royal. He's the former Master of Trinity College. He's was President of the Royal Society, and before that he's had a lifelong career in cosmology and astrophysics. And we're actually absolutely delighted, Lord Rees, that you could join us and kick us off this morning. And you're going to be speaking to us on AI and ET. We're looking forward to it enormously. Thank you very much. Let's welcome Lord Rees.
Right, well, thank you very much. It's a great pleasure to be here. I think I should start off by addressing a question which I'm often asked. Does being an astronomer give you any special perspective? Now, I spent my life among astronomers, and I have to say that the fact that they contemplate huge arrays of space and time doesn't make them any more serene than anyone else. They fret just as much about what's going to happen tomorrow and next week, etc., as anyone else. So it doesn't have much effect. But I think when they try to be philosophical, I think they do bring a slightly different perspective, which most other educated people don't have. And that's an awareness of the far future. So let me start off by explaining this. Everyone is familiar with the time chart of evolution here on the Earth. That's just a very rough sketch. We know that we're the outcome of about 4 billion years of evolution on the Earth, and we're all familiar with this. But I think most people somehow think that we humans are the culmination of it all. That it's been going on for 3 or 4 million years since the very first life, and we're the culmination. But no astronomer can believe that, because the one thing we know as astronomers is that the sun is less than halfway through its life. It's been shining for 4.5 billion years, but it'll be probably 6 billion more before it flares up and engulfs the inner planets and destroys any remaining life on Earth. So that therefore means that the potential for future evolution is at least as great as it is for the evolution we've had in the past. And if we consider any creatures sending this postcard witnessing the death of the sun, they will be as different from us as we are from bacteria. And I would argue that they will be actually even more different. The reason for that is that, as I'll expand on a bit later in this talk, future evolution is not going to be driven by Darwinian selection. It's going to be driven by technology. And that's much, much faster. It takes millions of years for new species to emerge, evolve, and die by Darwinian processes. But what's going to happen in the future, and this links to the robotics and AI, which is the theme of this meeting, is going to be developments taking place on a technological timescale. And that's much, much faster. And that strengthens the point I've just made, that even if we had just biological evolution, then we'd expect as much difference between now and the end of the sun as there is between the simplest life and us. But that's an even stronger conclusion. And so we just can't conceive the possible future developments here on Earth and far beyond. And that's really my theme today. But I think the strong message is that it is not reasonable, in my view, to think of humans as in any sense the culmination of anything. We may be nearer the beginning than the end of the overall emergence of complexity and wonderful things in our cosmos. And just to put this into perspective a bit more, there is, of course, the great acceleration. Supposing that an alien had been watching the Earth over its 4.5 million years history, which we haven't. We've had pictures like this for about 50 years, but the aliens would have seen over most of that 4.5 million years pretty slow changes. Continents drifted, ice ages came and went, etc. But then they would have suddenly seen more rapid changes in vegetation and other features on the Earth's surface, signaling the emergence of human civilization. That would happen over a few thousand years, accelerating just within last century. And in this century, they would have seen drastic changes when humans really started to affect the Earth's atmosphere and started to affect the biosphere, and they'd have seen something else quite remarkable. For the first time, they would have seen projectiles from the Earth leaving it, going up into space. Some going to orbit, some going to the other planets. So they'd have seen something special in this one century, after 45 million centuries had elapsed with nothing changing so fast. So this century is very special and is an acceleration, and that's why we can't really predict what is going to happen. And as I said, Darwinian evolution will be superseded by much, much faster biological evolution, by technological evolution. And an issue which I'll come back to at the end is, what is this evolution going to be? Will it be evolution of organic beings like us, or will it be superseded by electronic beings? I suspect, and we'll argue later, it's the latter, because there must be some limit to the processing power that's possible using the sort of kind of wet hardware we have in our skulls, and that limit does not apply to electronic computers, still less probably to quantum computers. So one scenario is that the deepest cerebrations made in the future by any kind of beings will be made not by wet hardware, but will be made by our successors, who are going to be inorganic. And I'll mention later how this may come about. Well, just to recap a bit about what's happened, and I know that Professor Wyatt talked a bit about this last night. I'm sorry I wasn't here, but of course we have seen very rapid developments in the capacity of machines to perform intellectual tasks. Now, of course, this in itself doesn't mean anywhere near being human, because we've had pocket calculators for the last 40 years that can do arithmetic much better than any of us. But of course, familiar landmarks are the IBM computer that beat Kasparov, the world chess champion. And that was 20 years ago. And then, and I know that you did hear about this, there's a famous Watson computer which beat the human contestants in this game show. I don't really know about this game show Jeopardy, but I gather it's not quite as mindless as the game shows we have on British television, and so it did indicate some genuine great breadth of knowledge that the computer was able to understand crossword clue type questions and come up with the answers. So that was progress. But then this year we had this other development, which was a computer which beat the world champion at not chess but the game of Go. Now, the game of Go is played mainly in Asia, and it is said by its proponents to be an even deeper and more complicated game than chess. And certainly it's one where the number of alternative moves is much greater. And a company called DeepMind in London, which is headed by a really amazing young man called Demis Hassabis, who is spearheading all this and is himself an enthusiast for Go, that managed to beat the world Go champion. And the point I want to emphasize is that what these computers are doing is very different from what the IBM Deep Blue was doing when it beat Kasparov. The reason was that the Kasparov computer was programmed by expert chess players in detail. Whereas what's happening now is what's called generalized machine learning, where the machine actually learns itself. And the DeepMind people 2 years ago made their first success when they trained a computer to play the old Atari computer games. That's not human. And they were just told, give an idea of what you need to do to score, and then they learnt, and eventually could play as well as a human player. And in the case of Go, they obviously gave the computer the rules in some sense, but then it observed lots of games, and it played against itself to get better, millions of games, and then eventually beat the world champion. And the important difference between this and the IBM chess-playing computer is that the programmers don't know how it made up its mind when it made one or two especially good moves. It made moves which surprised humans, and they didn't know because it had taught itself and was obviously in its program to develop algorithms which may not have been like what the humans would have fed into it. And so it made moves which were very surprising, but were in fact remarkably good. And so this is a sort of portent of things to come, that machines can learn in a way that doesn't require being programmed by experts. And this is also being used for machine translation. Of course, the early machine translations were slow. You put in the linguistics, the semantics and all that. Whereas what happens now is the brute force method. The best translations are done by letting the computer just read lots of texts in different languages and figure out how to translate. And for instance, they give the computer pages and pages, and one thing they use is EU documents. The computer never gets bored. But the big breakthrough came from being able to process not 1 million, but 1 billion pages. And it's really the ability to assimilate and process huge volumes of data which has allowed this technique of deep learning, which was actually developed by Jeff Hinton, a professor then at Toronto in the 1990s, that can now be realized because of the greater computer power. And so what we are now seeing is the ability of computers to really learn themselves and generalize tasks. And this is what opens up possibilities which are both exciting and perhaps rather frightening about the future. And Demis Hassabis, who is the pioneer of this, he's a very idealistic person. He thinks it's not too soon to have sort of regulation of AI development, just as we have regulation for biodevelopment. But he says he wanted to solve the world's problems, and he thought the best thing to do is to solve the problem of producing a machine of at least human intelligence, and then that machine will solve all the other problems. So you solve the machine intelligence first, and then that will help you to cure cancer and all the rest of it more quickly. So that's his motive. And I don't think he's crazy. This may be the right way to set about things. Because, as we know, there are these huge developments. This is the effective Moore's law for computers. You've all seen diagrams like this. But the point is, there's still quite a long way to go. It'll have to be a slightly different technique, because we're getting the maximum concentration of elements on a chip already, but there is a long way to go. Well, again, I don't want to duplicate what Professor Wyatt said yesterday, but I think we've got to realize that despite the huge, seemingly intellectual achievements of these computers, DeepMind's computers, robots have a long way to go before they can match human capabilities in any other respect. The computer that beat the world chess champion is obviously achieving some fairly powerful processing in its brain, but we know we can't make a robot that can move and recognize the pieces on a real chessboard as adeptly as a 5-year-old child. So we're a long way behind in having computers and robots which can interact with the external world and perform delicate movements. So that's far behind. And so it's naive to just extrapolate the processing power and think and what computers can do in that front, because if the robots are to really do the things that some people speculate about, there's got to be huge breakthroughs in sensors and in other kinds of technology. But of course, in terms of pattern recognition, face recognition, etc., they are making great progress. So my point is that within this century, we're going to see a transformation, and at the end of this century, there will be machines which have a larger range of human capabilities than present-day ones, and which vastly surpass human capabilities in some respects. And that's the challenge we have to face. Well, I'm now going to digress a bit because the title of my talk was about life and ET beyond the Earth. So I'm going to digress a bit and spend 10 or 15 minutes give you a little tour of the universe and then talk about space exploration. And since we're in Cambridge, I think I should start off with a picture of Isaac Newton. He was a student at Trinity College, and Trinity College, which is my college, has never had such a good student as him. It's been downhill all the way for the last 300 years. And of course, he famously provided the first unification of telling us why what makes the apple fall is the same force that holds the moon in its orbit around the Earth and the sun going around the sun, etc., the first unification. And Newton thought about space travel. This is a famous picture from the English version of his Principia, and you see what it shows. It shows a cannonball being fired from a mountaintop, and if it's fired fast enough, then its trajectory goes downwards no more steeply than the Earth goes away underneath it. It goes into orbit. This is still, I think, the easiest way to explain to students the concept of orbital flight. Now, Newton calculated that to go into a circular orbit, the cannonball had to be fired at 18,000 miles an hour, far beyond, of course, what was possible at that time, and it wasn't until 1957 that the Russian Sputnik was the first object to actually go into orbit in this way, followed 2 years later by some dogs, and then 2 years after that by Yuri Gagarin, the first man in space. And just as an anecdote about this, Gagarin came to Britain soon after his flight, about 1962, and was mobbed by enthusiastic crowds. And Macmillan, who was the Prime Minister at that time, Lord Cosmology, said it would have been twice as bad if they sent a dog in terms of public appeal. Only 8 years after Gagarin, we had this iconic picture, iconic among environmentalists, taken by the Apollo astronauts orbiting the moon, showing the Earth's delicate biosphere contrasting with a sterile moonscape where the astronauts set their footprints, and Neil Armstrong, one small step, in 1969. And I cherished this picture, signed for me a few years ago by 7 of the Apollo astronauts, showing a picture of one of the expeditions on the moon. But you've got to be middle-aged to remember any of this. The last men on the moon came back in 1972. And there's been no return to the moon, still less have people gone further. Had the momentum of Apollo been maintained, there'd have been footprints on Mars long before now. But of course, the motive for the Apollo program, the vast expenditure, was not scientific, it was to beat the Russians. And so there was a scaling back. And since that time, more than 40 years ago, humans have been into space, but only orbiting around in low Earth orbit. many in the International Space Station, which is, of course, far less exciting and glamorous. And I'm a bit cynical about this, to be honest, because the space station only makes the news when the Brit goes up, or when an astronaut plays the guitar in space or something like that, or when the loo doesn't work or something like that. It's not very inspiring. And this is because the scientific and practical case for sending people into space isn't very strong. It's getting weaker all the time with each advance in miniaturization and robotics. And despite the languishing of manned space flight, of course, robots and probes have explored all the planets of our solar system close up, and of course we depend on space technology in our everyday lives for sat-nav, weather forecasting, communication, etc. But let me give you a quick tour through the solar system and the planets. So here's Mars, the red planet, which is the first one you'd encounter if you go out from the Earth. This has been visited, among other things, by this robotic probe called Curiosity, which was got there about 4 years ago. It's about the size of a small car. It landed where the oval is on the top left of this huge crater, which is about 100 miles across, and it's been trundling across this crater for the last 4 years, and sending back lots of pictures. Here's one, and you can see the geological strata that it's been studying. Here's another picture it's shown, and we are learning a lot from this probe, and of course not as much as we learned from a human geologist, because it doesn't have the kind of artificial intelligence that you could put in today. Getting out beyond Mars, we get to Jupiter, the giant of our solar system. And there's been a probe just recently which is almost going into the atmosphere of Jupiter. But of course it's got these 4 moons discovered by Galileo in 1611. And these 4 moons are all very distinctive. There's one of them is Europa, which has an icy surface, and the other, Io, is a sulfurous and volcanic surface. So they're all very different and all fascinating. They've all been observed close up. Going out beyond Jupiter, we get to Saturn, famous planet with its rings. And it's been observed by a spacecraft called Cassini, which has spent about 10 years orbiting around Saturn's rings. And this is a very nice picture. It shows an eclipse of the sun by Saturn. The Cassini took this picture when it was beyond Saturn, lined up with the Saturn and the Sun, and the planet Saturn is blocking out the Sun, but the Sun is still shining on the rings. And that arrow points to where the Earth is. It looks very small, you can hardly see it. It's a long way away now. This Cassini probe carried in its cargo bay a smaller probe called Huygens, built by European scientists, including many at Open University, which was supposed to land on Titan, one of the moons of Saturn. And what it was supposed to do was shown in this artist's impression. Titan was known to have an atmosphere, and it was going to open a parachute and land on the surface. And it did just that. On the left and the center, you see 2 pictures taken on the way down. On the right, you see where it landed. Now, it looks rather nice. There's rivers and a little lake, etc. But the temperature is minus 180 degrees centigrade, and this liquid is not water, but liquid methane. So this is not a very clement environment. So this is Titan, the giant moon of Saturn, and Saturn has another moon called Enceladus, which is much smaller. This is a close-up of this, and rather like Europa, this is covered in ice. There's good reason to believe that there is actually a deep ocean under this ice. Other things we've learned from robotic probes, which have been in news in the last couple of years, the European Rosetta probe to the comet, We've seen pictures like this taken by that, and this little robot which landed on the comet. And also, we have had in the last year pictures being back from Pluto by this American spacecraft called New Horizons. And here's a picture of Pluto. Here's a rather better one. Pluto's got more active geology than people expected. And this is a picture of Pluto and its moon, Chiron. Now, these are remarkable achievements of robotics because these pictures are beamed back from Pluto, which is 10,000 times further away than the moon. And the other thing, which is deeply frustrating to those who designed Rosetta and New Horizons, is that the technology on these things is at least 15 years out of date. Because both these probes took 10 years on their journey to their remote destinations, and of course you've got to fix a design several years before you actually launch something. And so one can imagine how much better one could do with miniaturized probes by being able to use the latest technology. Just think how smartphones have changed in the last 15 years, and imagine how much better you can do. And there are plans to launch huge swarms of spacecraft to the outer planets. And I think what will happen in the next 50 years is that the whole of the solar system will be explored by miniaturized intelligent robots, sort of super versions of the latest iPhones, as it were, in very large numbers, sending back data from all over the solar system. Another thing that's going to happen, I think, is large robotic fabricators building big structures up in space. We have the possibility of having robots which are intelligent enough to actually assemble things, and that'll be a big breakthrough, because the trouble is that you have to launch everything in a nose cone of a rocket, which limits the scale, but one can imagine building huge, very, very gossamer thin mirrors and for solar energy and astronomy up in space, and all these kind of things. Maybe mining material from the moon or from asteroids to do it. So large-scale construction, again using robots, will, I think, happen in the second half of this century. But will humans follow the machines? That's the next question. Well, here's a picture going back to the Apollo program. This is Harrison Schmitt, Apollo 17, when the last two men on the moon, on this moon buggy, and this is more than 40 years ago. And so what is the likelihood that humans will go back into space? As I said, the practical case is getting weaker all the time with each advance in robots and miniaturization. But I personally think that as a human being, one would like to think that there will be people walking on Mars and maybe on asteroids, etc. But how is this going to happen? My personal feeling is it won't happen in the way Apollo did, or in the way that NASA and ESA are doing manned spaceflight, because that's very expensive. It's very expensive because these agencies have to be highly risk-averse in launching publicly funded civilians into space. If you remember the shuttle program, it was launched nearly 140 times. There were two big disasters when it blew up. Each of them was a big national trauma in America and held up the program for about 3 years. But a 2% failure rate is quite acceptable to test pilots and to many adventurers. So my personal view is that the first people to set foot on Mars will be privately funded adventurers who are prepared to accept high risks, maybe even one-way tickets. There will be people prepared to do this. And so I have in mind people like Sir Ranulph Fiennes, the great adventurer, who at the age of 70 or so dragged a sledge across the Antarctic in the winter and things like that, and has taken huge risks. People like that, and the guy who fell supersonically from the high-altitude balloon, and things like that. The people prepared to take high risks, and adventurers, and they're the sort of people who will go to Mars, and they will be privately funded because the other thing that's happening is that there are companies, especially in the US, which are developing rockets which will be able to send people, and again, because they're privately funded, they can accept higher risks. One of the best known is SpaceX, run by Elon Musk, who also develops the Tesla electric cars. He's a great enthusiast, and he has said that he hopes to die on Mars, but not on impact. And he's now, I think he's 44 years old, so 40 years from now, there might be a small community on Mars. But these people will be a sort of community of sort of bold pioneers, not sort of ordinary people, rather like the typical astronauts who talk in acronyms and are very sort of they're very concerned with safety. Now, what will happen then? Let's suppose that we do have communities of people living away from the Earth 100 years from now, which is quite likely. There will, as I say, there will be these rather sort of adventurous people, those who do crazy adventures now, and we know there are people, and I think we will cheer them along, we admire them, even if we don't want to follow them. Because incidentally, it's a really dangerous delusion to think that we can solve the world's problems by mass emigration. There's nowhere in the solar system that's even as clement as the top of Everest or the South Pole. So we've got to solve the world's problems here. Space is just for adventurers. But these adventurers out in Mars, they will, of course, as humans, be very ill adapted to this environment with different gravity, different atmosphere, etc. And I think we would wish them good luck in using all the resources that will be available in 50 years or so in the realm of both genetic modification and AI and cyborg technology to adapt to this alien environment. We may, and that's one of the themes of this meeting, want to have some ethical constraints on such developments on Earth, both in the AI area and also in the bio and genetic modification area, but these people will be beyond the realm of any terrestrial legislators, and we wish them good luck, and they will have any motive to do this. Because if you're under 0G, it's better to look like a spider than like a human being, so they really change. And so I think that if we have a community living away from the Earth by the end of the century, which is not crazy, I think it's quite likely, then they will use all these technologies to adapt their progeny to this alien environment. And so the post-human era is going to begin not here on Earth, but away from the Earth, where there are no ethical constraints and a stronger motivation for adapting to something new. And so that, I think, is what's going to happen. And, of course, it's going to be something which happens in a few centuries. And to go back to what I said earlier about the time spans, let's remember that we're talking about just what might happen in a few centuries, and there are tens of millions of centuries ahead. And so just think of how inconceivable the developments will be beyond that, because these post-humans, which may be organic, but more likely, I suspect, inorganic, that they'll be able to spread far beyond the solar system. If you're near immortal, then a journey lasting thousands of years is in no way daunting, and so they will spread to the other stars, and so that is the future. And as I said, the Sun has about 6 billion years ahead of it. It's less than halfway through its life, but the entire universe may go on forever. And to quote Woody Allen, eternity is very long, especially towards the end. And so my view is that the future will be immensely complicated entities which will not be human, probably not organic, spreading from the Earth through space. Well, the next question is there life out there already? I've made the point that even if there isn't, then life descended from humans can spread everywhere through space in the future, the long-range future. Well, no one expects any very advanced life anywhere in our solar system. There may be some freeze-dried bacteria on Mars, and there could be something swimming under the ice on Europa or Enceladus. We don't know. That's quite possible. It's worth looking. But no one thinks there's any advanced life. But the perspective changes when we look beyond our solar system, beyond the range of any probe we can now construct, to the realm of the stars. And here there's been a transformation in the last 20 years, one of the most exciting things happening in astronomy. Because we've realized that most of the stars you see in the sky are, like the sun, orbited by retinues of planets. And we now have evidence about these. The planets are in general too faint to be actually detected directly, but there have been two techniques used to infer the presence of the planets. And let me just mention, they're quite simple. The first is illustrated here. If you have a planet going around a star, then what's actually happening is that both the star and the planet are orbiting around the common center of mass, the barycenter. The planet goes round in a big orbit, and the star, being much heavier, goes round in a smaller orbit. And even though you can't see the planet, it's possible to detect the small motions of the star, very small change in the Doppler effect by taking the spectral lines, and the star will go around. And here's an example where they've taken measured the velocity of the star wave from its Doppler effect and found it changes periodically. And this sine wave indicates that this star is orbited by a planet in a circular orbit. And the amplitude of this is a few meters per second, so that you can detect motion of a star of about walking pace out of this, and that's induced by a planet. From data like this, you can infer the length of the planet's year from the period of its orbit, and you can also infer the mass of the planet from the amplitude, because the amplitude of the star's motion is proportional to the mass of the planet. So this technique has led to the discovery of hundreds of planets, but mainly big ones, because for an Earth-like planet going around the Sun, for the Earth going around the Sun, the motion is only a few centimeters per second. That's very hard to detect. But there's another technique which has been able to discover planets of lower mass than this so-called radio velocity technique. And this is even simpler in principle. The idea here is if we happen to be looking in the plane of the orbit of the planets, then when the planet moves across the face of its star, like the transit of Venus, which we observe here, then we can't observe this in high resolution, but if we look at the star, we will find that the star will dim a bit when the planet moves in front of it, because it blocks out a bit of its light. And for instance, if you were from a huge distance observing the Earth moving across the Sun would get fainter by 1 part in 10,000. When the Earth went past. So what you look for is regular dips. And from the depth of the dip, you can get the size of the planet, and from the frequency of the recurrence of the dip, you can get the length of the planet's year. And this technique has been used by a spacecraft called Kepler, which has looked at 100,000 stars with, repeatedly with enough photometric precision to detect changes in the brightness of this side, to discover literally hundreds of planets. And this is a rather sort of silly depiction of the data, where this actually shows all the data where it shows the length of the day, the length of the year, and the masses there. But it just indicates there's lots of data. Special interest, of course, attaches to planets like the Earth. Like the Earth in two ways. First, with a mass about the size of the Earth, so gravity and the atmosphere might be similar. But secondly, at a distance from their parent star, such that the temperature allows water to exist, neither boiling away nor staying frozen all the time. And some of the planets discovered by Kepler do answer that description. That they are planets where life could exist. And you may have seen this just 2 weeks ago, there was evidence for a planet a bit heavier than the Earth in the star Proxima Centauri, which is the nearest star. This planet is in the habitable zone, but the star it's around is a very small, faint star, and so its sun is about 100 times fainter than our sun, and it's in an orbit of about 10 days period. But that gives you about the right temperature where water could exist. But we'd really like... sorry, how much longer do I have? I ought to stop fairly soon, but let me...
Perhaps another 10 minutes?
10 minutes, okay, yes, okay.
I think we're all fascinated.
Okay, well, yes, okay. Okay, well, let's go on. Okay, so 2 things. First, we would like, of course, to observe these planets, not just their shadows, as it were, and that's very hard. To imagine how hard, let's suppose that there was some alien astronomers with a big telescope looking at the solar system. Then the Earth would look like a tiny pale blue dot, in Carl Sagan's nice phrase, very close in the sky to its star, our sun. You're looking for a firefly next to a searchlight, as it were, and that's very hard. But if the aliens had a big enough telescope to observe that pale blue dot, they could learn something about the Earth, because the shade of blue would be slightly different depending on whether the Pacific Ocean was facing them or the landmass of Asia. So they could infer the length of the day and that there were continents and oceans and something of the climate. We can't do that yet, but the European Southern Observatory is building a telescope which is unimaginative. It's called the Extremely Large Telescope, the ELT, and this will have a mirror 39 meters across, and that's, I guess, more than a bit more than twice the size of this room across, a mosaic of 800 pieces of glass, and that will be able to do these sorts of observations for planets around nearby stars. And as I said, we expect that there are many, many habitable planets in our galaxy, in our Milky Way, probably about 1 billion Earth-like planets altogether. And if we bear in mind that there are billions of galaxies in the universe, this is a small patch of sky, and each of those smudges is a galaxy like our own. Let's think how many potential those there are for life. But what we want to know is there life on these? We don't know. And the reason we don't know is that we don't understand how life began on Earth. We understand Darwinian evolution, but the basic transition from complex chemistry to the first metabolizing, reproducing system is not understood at all. But I think the good news is that this is no longer put by biochemists in the too difficult box. There are now serious people attacking this question. And so I'm hopeful that within 10 or 20 years, we will know how life began on Earth, and whether it's in undersea vents or in Darwin's warm little pond or where. And if we have that understanding, it'll tell us 2 things. It'll tell us first, is it a rare fluke, which wouldn't be expected to happen elsewhere, or would we expect life to at least get started in lots and lots of these Earth-like planets? Second, it'll tell us, is the chemistry of DNA and RNA really special, or could there be other chemical bases for life? Could there even be sort of methane-based life on Titan, for instance? We'll learn that sort of thing. But even if simple life turned out to be widespread, and you could perhaps learn that because you might actually detect some of these planets looking green, for instance, with the big telescope, that's not the same as there being intelligent life, because as we know, there are many vicissitudes on the way from simple life to intelligent life, and evolution biologists debate whether if you were to rerun evolution, would you get to something like humans or not? Or would you end up with a planet just covered in ants or something like that? We know that the death of the dinosaurs allowed mammals to emerge. What would have happened otherwise? So we don't know the likelihood of simple life leading to complex life. at all. But it might, and for that reason, there have been attempts over the years to see if one can find any evidence for technological life. Just by analogy with the Earth, it's worth a search. No one's very optimistic, but it's worth a search. There's a new project which actually I'm involved in called the Breakthrough Listen Initiative. And this is bankrolled by a Russian investor called Yuri Milner, who's going to commit $100 million over the next 10 years to various searches for artificial radiation coming from space. And although this is a gamble, I'd rather he spent his money this way than on a big yacht or on a football team, which is what many of his ilk do instead. So he's doing this, and I chair his advisory group for this project. And what's being done is to buy time on some of the world's best radio telescopes, to develop a spectrometer to look for very narrow band signals, to divide the spectrum into 10 billion different channels with very narrow bands, and also to have a project look for optical flashes, because we've no idea what we're looking for, but the exciting thing would be to look for any kind of signal which is manifestly not natural. Now, if we did detect something, what would it be? And here I go back to what I said at the beginning. We've no idea, of course, what it might be. We should look for everything. We should look for artifacts of all kinds, as well as radiation of all kinds that can't be natural. But if, in any sense, the life on another planet tracked what had happened on the Earth, then what we would expect would be silence for billions of years, then a brief period of technological civilization, followed by billions of years, if it didn't snuff itself out, by the electronic descendants of that civilization. And that therefore leads me to suspect that if this program detects anything, it won't detect a civilization, won't detect anything organic, but it will detect some byproduct or malfunction of machines spreading through space, which are perhaps the creations of some long-dead organic civilization. Because it's most unlikely that if we catch evidence of intelligence on other planets, that it will be synchronized to within a few centuries, so that we would see the organic civilization. Far more likely that it's either many millions of years behind, in which case we see nothing, or many millions of years ahead, in which case we will see the robots and not the humans. So this is my reason for thinking that what we will see is probably electronic, not organic, not from civilization, and probably therefore not a decodable message. But it will be important to find any evidence for something which is manifestly artificial coming from space. Well, just to close, I wanted to bring things back slightly closer to here and now, and bear in mind that from what I've said before, even in this perspective, concertina perspective of billions of years in the past and in the future, our century is special. And I first discussed this in a book I wrote about 10 years ago called Our Final Century. I put a question mark in, but the publisher left out the question mark. But the main point is that we have entered a period called the Anthropocene, where one species, ours, can affect the whole planet in a way that was not possible before. We're now more numerous, we're more empowered, and what happens this century is going to determine whether we snuff out or provide a big setback to civilization on the Earth if we handle things badly, or whether we are the generation that triggers a transition from organic life to intelligence embodied in other forms that could spread through the universe in the future billions of years. So either way, this century is special, and we're stewards of this planet this is a very special place at a special time, and that I think is a good message to end this talk on, whether you're astronomers or not. So thank you very much for listening.
Thank you very much, Lord Rees. Are you happy to take questions? Wonderful. We have a roving microphone, so if you put your hand up, and Alexander will bring it to you. Mickey, thanks.
Thank you, Lord Rees. Very, very interesting. The question I want to ask is, can we extend Fermi's conundrum that if the universe is full of life, where are they? Can we ask, where are the robots?
Indeed we can, and that's a genuine issue, that if indeed life is widespread, then it is rather surprising that there's as yet no evidence. And we should look for all kinds of evidence, but it's true that is indeed a constraint, because there is a scenario which I've just outlined whereby one civilization could spread its effects through the galaxy. And so indeed, I think one could argue that the famous Fermi argument does suggest that we shouldn't be too optimistic about the SETI searches revealing anything. But on the other hand, there is a former lecturer at the Open University called Stephen Webb, who wrote a book with 50 counter-arguments to the Fermi paradox, 50 ways of getting around that. And he has a second edition, to which I wrote a preface, with 75 arguments. Now, you could say one good argument is better than 75 feeble arguments, but nonetheless, I think you're quite right that the fact that we don't see these aliens staring us in the face is, of course, a constraint on the future scenarios. Yes.
Thank you very much. The current situation is that the robots assist us. In the future, do you see that we're going to be assisting the robots, or that we will cease to be?
As I say, I think the question is whether there will eventually be a transition from the sort of brains that we have to the sort of brains that computers have. And I think it's quite likely that that transition will happen at some stage. I think it'll happen first, as I mentioned, away from the Earth, where there's a big pressure for it, and we may try and constrain it here. So I think even though the machines may surpass humans in more and more respects, it could very well be that organic life still survives on the Earth. We don't know. But I think the scope for further biological evolution is more limited than for electronic evolution. But of course, even human evolution is going to be not natural selection. It isn't natural selection now, but it will be genetic modification, etc., here on Earth. And so people on Earth will become cyborgs and be modified, but there will be ethical constraints on that. And as I say, there'll be less motive for that on Earth than there is in space.
I'd like to pick you up on that, because you talked about there being no ethical constraints on these artificial communities outside of Earth. But in some senses, that will be an evolutionary process then, because presumably they will start with some ethical constraints that Earth wants to introduce there, or
yes.
How do you think the ethics?
Well, of course, they could decide that it is wrong to go this way, but all I'm saying is that if they decide otherwise, then we can't stop them, and they have a motive. I mean, I should say, just to digress, that I'm very, very worried about the effects of particularly biotech on Earth, because it's getting very dangerous, and there are ethical constraints and there are regulations, but I'm worried that we can't enforce these regulations globally any more than we can enforce the drug laws or the tax laws globally. And I'm worried that anything that can be done will be done somewhere by someone on Earth. I'm really scared by that. That's my biggest worry about the next 20 years. But I think, talk about people in space, then you may think that then the ethics are rather different if they're trying to live away from the Earth. So that's why I think that these techniques will develop faster there.
Right at the very back, and then we'll come forward to John.
Thank you very much. Delighted to see you in person after seeing you and reading elsewhere.
Can you hold the microphone?
Yes,
really
a bit louder,
close?
yeah.
Is it okay, better?
Yeah.
So SETI, the search for extraterrestrial intelligence, has been ongoing for many years. I don't know exactly how many, but for a number of them. I don't think anything of any remotely interest has been actually identified. And if let's assume, as a thought experiment, that we continue searching and listening for the next 100, 200, 300 years, and if nothing interesting comes up, what would be your, philosophical, theological conclusions?
Well, of course, as you say, searches have been done, but these ones that will be done by the Breakthrough Initiative will be, they'll do in a day more than the total amount to be done up to now. So they'll do more intensive searches, will search in new ways. But, of course, if they may not find anything, and of course, if as 100 years from now nothing's been found, then of course that will change the odds on there being anything. But and I think there are two maxims that are important in this game. One is extraordinary claims require extraordinary evidence. You need a lot to be convinced. But the second one is that absence of evidence isn't evidence of absence. So there could be intelligence in some contemplative form that's not sending out any kind of evidence of its existence. So we can never be sure that it's not out there. But of course we can constrain it if we search deeper and deeper and still don't find it. And I think we've got to bear in mind that the uncertainties now are such that it could be that life is unique to the Earth, or it could be that there is a galactic club out there that we could be late joiners of. We just don't know. Either is possible. The uncertainties are so huge.
John had a question.
Thank you so much. Wonderful talk and mind-expanding, mind-blowing. Just a comment on that great phrase, extraordinary claims require extraordinary evidence. It reminds me of a story I heard of Bertrand Russell, who was asked what would happen if after death he woke up and discovered there actually was a God out there. And Bertrand Russell said, well, I say to God, there's not enough evidence, God, not enough evidence.
Yes.
But what I... this sort of mind-burning narrative of over billions of years, and particularly the rise of artificial intelligence, this idea that artificial intelligence may in some way be our mind children, they will take us on into the future, raises the whole question about what it means to be human, which is really the focus of our conference. And, and one of the questions it asks anew, it's not a new question, but it does ask it in a new way, is what are human beings for? Now, I know that's not a scientific question, but I'd just be interested in your responses to that question. What are human beings for?
Well, I mean, I think if I was to be formal, I'd say it's a question I don't understand. But I think I would say that we are on this wonderful Earth and with huge potentialities, and as I said, we are alive at a very, very special time when our role in the cosmos could be non-trivial. But also we are humans and we have human characteristics, and just as a lion has a way of expressing itself, so do we as humans. So we are unique in our capacities, but all I'm saying is that we are almost certainly not the culmination, and we should not think that we're the purpose of creation. We are a step on the way.
Thanks,
Behind you, Nigel.
Thank you very much, Nigel Carroll. Martin, thank you very much. This is wonderful to hear you put some of these pieces together, having met, talked, and having obviously read your, I think, very largely ignored, wonderful little book. Of course, in the States, it's called Our Final Hour. Which
yes, that's right, yes.
This is really getting pretty scary over there. Americans love being scared. I mean, what interests me, not least in reference to this $100 million from the Russian philanthropist, who decided not to buy the football team, we're moving increasingly into private funding and private initiative here, Elon Musk and so on and so forth. At the same time, there does seem to be a continuation of this general disinterest on the part of the US and the other major Western powers in remotely beginning to build on what was achieved back in the 60s. Because at one point in mid-60s, NASA got 5% of the entire US federal budget, which is 10 times what it gets now. Do you have hopes that governments are going to become at least more interested in tracking these developments, which seems to me ultimately to be central to a sort of proper private enterprise in this area? So far, as you say, it was a Soviet issue which really drove that extraordinary thing with Neil Armstrong.
Yes.
Are there signs of a more mature, longer-term approach on the part of Western governments? Thank you.
Well, let me first say that if I was an American, I would not support a huge manned spaceflight program. I would leave it to the private sector. But I think as regards support for science and technology, I think it is important to bang the drum that advances in science, whether it's AI or biotech, are crucial, and of course the public sector is crucial. It's been pointed out often that all the key elements of an iPhone arose from public sector research, either in universities or funded by the American Defense Department, and so we've got to keep that going. But as regards manned space flight, I mean, I personally think that is something which probably isn't a priority for major public expenditure, because as I say, it is just an adventure and a spectator sport. So I'm happy to leave that to the private sector. I think that's all I would say on that. But incidentally, regarding the search for extraterrestrial life, which of course is very cheap, this has been funded by a succession of private benefactors. There's no government money. And actually, I would support the idea of some public money to supplement this, because, to put it this way, it's a subject which fascinates people. I mean, if taxi drivers learn astronomy, the first thing they ask is, are we alone, you know? And I would say two things. If you were to ask people coming out of watching a science fiction movie, would they be happy if some of the tax revenues in that movie were hypothecated for a SETI search? I think enough would say yes to justify 100 million. And also, another example, if I was an American and I had to go before a congressional committee to justify expenditure on science, I'd be happier justifying a SETI search than justifying money for a big accelerator, because there's far more public interest and far more likelihood of big surprises. So I think it should be regarded as something which is so potentially interesting that even though, even Frank Drake, the great high priest of this, who's on our committee, he would bet 3% of finding something. But nonetheless, it's so important, and it would so transformative, that it's worth the search to have a chance of it being discovered in our lifetime. Yes.
I want to go back to the sort of topic a little bit. In sociology, one of the things you teach undergraduates is that when people are playing a game, what's significant about a game is that you teach children to stop playing a game, and that the art of being intelligent is knowing when it's just a game and when this is normal life. Yes. And for sociologists, this opens up the idea that intelligence is a label for what you do with other people, not something that a machine can do. And sociologists will argue that games are demonstrations of machine-like reasoning. And all these examples for me, and in fact my entire career has been dealing with these sorts of concepts, are certainly the genius of machines for undertaking game-like behaviour, but the lack of machines' capacity to make that leap to a social moral code, or personhood, as was mentioned last night. But this leads me to ask whether you need to use the label intelligence for the machines that are sent out to do our work. We might be staying at home and no longer playing games with one another and talking about other things. Yes. And we have machines going forth for us. What's the benefit of using the word intelligence for them? Because all the cargo that comes with it.
I agree with you that it is misleading, because clearly these machines can do some things better than humans, but all the other things that humans do is they're nowhere near being able to do. So I agree that it is it's misleading to imply that because they can do as well as humans in some arenas that they're anywhere near humans. I completely agree with that, and so perhaps one should use a different word. I mean, robotic fabricators is the word I would use for these things that might go into space. But nonetheless, I think, as you know, better than me, there is a debate, and I was just reading an excellent book with a big paper by Chalmers, you know, the guy who took consciousness, with about 20 responses by other philosophers too. A fascinating book on just the kind of questions of whether the issue of personal identity and whether a machine can be said to be conscious, whether you could download your brain into a machine and still call it you and all that. These are genuine philosophical questions which we may actually face one day. They're far, far beyond what we can do. In fact, the diagram I showed about the capacity of computers now shows that although they can do these marvelous things, they're about at the level of an insect brain, no further. So there's a long way to go. But nonetheless, it's not crazy to think that these things will happen, and it's not premature to start worrying about them. And the philosophical questions, I know you probably know the work of Chalmers and people like that, and Searle and all that. There's a debate about whether consciousness is an emergent property above a certain level of complexity, and whether it isn't. And also the question arises of if these machines, AIs, powerful machines, are developed, then how do we cope with them on the Earth? I mean, clearly, a powerful machine simply gives its owner a huge advantage if they're able to predict the future better than others, because the reason that the hedge funds rip off the rest of us is because they have these machines that can make better predictions. And if you have a sort of supercomputer, even better than the leading quant hedge funds have, then that will have a big advantage over everyone else, and that'll be dangerous to society if that's not controlled. But even worse, of course, is when these computers are not in a box, but can interact with the external world, especially if you have the Internet of Things. And this, of course, leads to all kinds of risks of error and mistake and runaway problems. And people have written about this. The person who's written the best book is Murray Shanahan, a professor at Imperial College, who's written about sort of artificial intelligence and how you can try and instill values into computers. And of course, the issue is that you can't codify all our values, but can you get a machine to actually learn our values by observing people? Now, of course, there's a problem there, but of course the ethics you'll develop depends on who you observe. But there is a genuine problem about that, and it's very hard to program the correct ethical behavior in sufficient detail to avoid serious malfunctions. I mean, a simple example people give, which is not too far in the future, is the robot that looks after your house and your kitchen, keeps your fridge stocked up, and cooks your meals for you. And if it finds there's no meat in the fridge, it'll put the cat in the oven and cook that. You know? Because the point is that a machine of the kind that is a feasible kind of robot we could have in the kitchen would obviously have no feeling that that was not the appropriate thing to do. It's obvious to human beings, but the question is, can you feed in a program all those eventualities, or can you make sure that the computer actually learns enough about human behavior and what humans do and don't do to avoid doing things of that kind? That's a serious problem, and that's, I think, going to happen within the next 20 or 30 years, because it doesn't need to be a sort of superhuman computer to be able to manage the household in that sort of way.
Thank you. There was a question here. I think, Andrew, this will have to be the last question. Just here at the front, Alexander.
Oh, yeah.
Thank you. You said that it's not reasonable to think of human beings as the end of evolution or of anything else. I wonder if you'd like to speculate about what the next steps might be, and whether they are for instance, to a combination of organic and inorganic, or where are we going next? in your view?
Well, I think, as I said, away from the Earth, I suspect a quick shift towards the inorganic, because the environment there is not suited to organic creatures anyway. But here on Earth, I think there'll be, depending on the ethical constraints, there'll be genetic editing, modification, and there'll be some sort of cyborg technology, even though there may never be possibility of actually connecting extra memory directly to the brain. I think that's the sort of thing that is going to happen. But I think in the far future, we just can't predict, because and I think as a scientist this has implications, because I think what is amazing, really, I think what humans can do is that our brains haven't changed very much since our ancestors walked on the African savannah and learned to cope with the everyday world, but we've managed to make a good deal of sense about the micro world of the quantum and the macro world of the cosmos, even though these are counterintuitive and don't follow common sense notions. So it's amazing how far we've got. But nonetheless, I think we've got to bear in mind that our brains may be limited, and there may be deep aspects of reality which are as far beyond us humans as quantum theory is beyond a chimpanzee. And so, we think we're making huge progress, indeed we clearly are, but there are concepts which clearly we can't conceptualize because our brains are limited, and that may have to await some post-human species, whether that will be organic, with better brains, or not. I don't know if you know that. I'm just to amplify it with a footnote. When I made this point, do you know the book of David Deutsch? He's a pioneer of quantum computing, but he really, I recommend his books. It's wonderful. But he criticized me by saying that in principle anything is computable. So there are really no limits. But I think that's not true, because what I meant was the limits to what we can conceptualize in our brains. And I'll give one simple example. If you've done coordinate geometry and I say, can you visualize the shape x squared plus y squared less than 1? Then that's a disk of radius 1, okay? Whereas if I don't know if you know what the Mandelbrot set is, but if you do, that's an infinitely complex pattern which is described by a simple algorithm, which you might have learned. And there's no human being who, given that algorithm, can immediately visualize the Mandelbrot set in a way that most people can visualize a disk if they've done any coordinate geometry. And so that's what I mean by saying, look, limits to the capacity of the human brain to conceptualize and visualize things. And there may be very important aspects of reality which will never be within human scope and will have to await post-human. But as I say, there's no reason to think that we are the combination.
Okay, well, thank you. On that note, looking into the far future, which none of us will see, and I don't know whether... One question I had is, are we glad that we don't actually know how it will work out, or would we really like to sort of actually be able to look into it?
Well, it's very interesting, because I had an op-ed in the Financial Times about a year ago on this sort of thing, and it was interesting, the reaction. It was rather bimodal, because I said that I thought the machines would take over and spread through the universe, and some people said, well, isn't it wonderful to have these things with deeper self-awareness and all that, whereas those who thought that consciousness was limited to our kind of hardware thought, isn't this bleak just to have these zombies and nothing there to appreciate the universe? So one's attitude towards this future does depend crucially on whether you think consciousness is an emergent property or whether you think that it is something which is peculiar to humans. I think that makes a big difference to how we think about this future. But of course, what we think about is irrelevant to where it is. And there's no reason to think that the universe is the way we like it to be.
Thank you very, very much, Lord Rees. You've stimulated our thinking and answered our questions well, and we're delighted that we've had you here this morning. So let's just thank Lord Rees again.